This tutorial is about voltage dividers. A voltage divider circuit uses resistors to reduce voltage. You can use voltage dividers to do a lot of things, like create a volume control circuit or generate reference voltages, and much more. If you apply Ohm's law, you'll find that 1 volt spread across 2 equal value resistors gives you half a volt in the middle, so you're getting half the voltage. And as you would expect, 4 equal value resistors would give you a quarter volt, half a volt, and 3/4 of a volt. For the sake of simplicity, let's stick to 2 resistors. If you use 2 resistors of different values, the voltage gets divided up in proportion to the amount of resistance there is. In this example, with 20% of the resistance on the bottom, you get 20% of the input voltage on the output. If I flip the position of these resistors, now with 80% of the resistance on the bottom, you get 80% of the input voltage on the output. Incidentally, voltage dividers will work just fine with both AC and DC input voltages, and this is the equation that you want to use to calculate the output voltage depending on the resistors you're using. And if you're not getting the output voltage that you want, well, try the equation with some different resistor values, or rearrange the equation. Alright, here's some more examples. Here I'm taking 10 volts and dividing it down to 1 volt. Here I'm taking 5 volts and dividing it down to 4 volts. And here I'm taking 100 volts and dividing it down to 1 volt. You might have noticed that I'm using massively different resistance values here, sometimes a few ohms, sometimes a few mega ohms, but it is ultimately the ratio of the resistance values that determines the output voltage. Now, that doesn't mean that when you build a real-world voltage divider you should use low-value resistors. Whenever you create a voltage divider, you have to be aware of the overall power consumption of the circuit, and you calculate it using this equation. With this circuit, the resistors are dissipating 0.1 watts, which isn't very much, so everything is fine. But in this circuit, the resistors are dissipating 1,000 watts, so the resistors are going to catch fire. The output voltage is the same in both cases, but the power consumption is totally different.
Alright, so we learned a little bit about safety there, about, not getting shocked and fried by electricity by having too much current running through your body. And so I just want to reinforce the idea of the V equals IR, voltage equals current times resistance. And I know we saw that in that past video, but I want to reinforce the idea of what this equation means, what it implies about how circuits are relating, how circuits are working. So again, V is electric potential voltage, as you see in the symbol for the battery. On the right here is just a brief chart of some common symbols that you'll see in electrical diagrams, circuit diagrams. And typically the longer plate in a battery cell denotes the positive side of the battery, and the shorter one's the negative. And so conventionally current flows, we say it flows from positive potential to lower, from higher potential to lower potential, or from positive to negative. But remember, as the guy pointed out in the previous video, the electrons are actually flowing the other way. So you don't have to worry about that, because everything we do is going to be in convention. But just remember that the electrons are actually kind of flowing in the other direction. Also pictured here are resistances as light bulbs. Remember that we force electrons to flow through resistances, and most of the time we make them do work for us, such as lighting up a light bulb. And as the equation implies, the current and resistance are inversely related. So if you have a greater resistance and a fixed voltage, then the current flowing through your circuit is going to be lower. And we'll go over that when we touch on voltage dividers again. It'll make a little bit more sense. So let's move on. One thing I want to talk about is measuring voltages, because remember, that's how we read signals in the analog world. We want our Arduino to read voltages and do something with those signals, right? I mean, that's what signals are. It's signals, for at least for our purposes in this camp, are changing voltages or changing pressures or changing electric potentials. However you want to say it, it's changing voltage. Okay, and so how do we measure a voltage? How do we measure a change in voltage? And well, we do it with a voltmeter. So here's a symbol for a voltmeter, and is this voltmeter configured right now in this electrical diagram to measure the voltage on the circuit? What about now? Is it now? Okay, no, definitely not. So we need to go back to the idea of the circuit, goes around in a circle, and it has to have a source of electric potential, and at the higher electric potential, at the highest electric potential will be where your source starts, and then you'll drive some sort of load, and there will be what we call voltage drops across the load, across the resistances. And after there's a series of drops across the resistances, the electric potential must return to zero on the other side of the battery, or other side of the electric potential source. And also, all of the voltage drops that when you go around the circuit, all the voltage drops need to add up to the total voltage drop across the battery. You can see this in the diagram to the right here, and kind of think of it, again, we like to use this ball analogy, or like, remember we used the Roadrunner and Wile E. the Coyote a couple videos back, where you can think of it as, regular old potential energy from physics class or from science class. When you pick up a ball, you exert kinetic energy, and you give off kinetic energy to the ball, and you're storing that kinetic energy in, among other forms, you're storing it mainly in the potential energy you gave the ball when you lifted it up. So this total drop shown here on the right is like your electric potential. That's the highest electric potential the ball has, or the highest potential energy the ball has, or you can think of the ball as an electron. Okay, and then the ball is going to drop, or in the electric case, the electrons are going to drop across the resistance, and the total drop, so if you have two drops, like two resistances, the total drop at some point, when you come around to the end of the circuit, you have to reach ground. You have to reach zero electric potential. And so that's like the ball eventually falling to the ground, where it can't give off any more kinetic energy. It's already spent all of the potential energy you gave it from the start, where it had its highest potential energy. So the question is, we want to measure electric potential, and in this case, what if we want to do it at a given spot on the circuit? So the probes, as you should note, should always, when you're measuring voltage, are connected in parallel to a circuit. And I'm not going to delve in deeper as to how the voltmeter is actually working, the internals of it. If you want to know and you have some time, come and ask me or ask a mentor, and we'll tell you more about what's happening inside the voltmeter. But for now, you need to know that it needs to be connected in parallel. And the basic idea is that probe 1, or it doesn't really matter, because you're measuring the potential. The polarity is not a huge deal. You'll just get a negative sign if you hook it up backwards. But probe 1 is placed at the point that you want to measure the potential, and you want to usually measure your voltage with respect to 0 volts or the ground. So the other probe is connected to where there's 0 electric potential, which we call ground. And so now that this is hooked up, the probe number 1, the one going to in between the light bulbs, so it's measuring the potential across that light bulb for reasons that deal with the internals of the voltmeter. But this goes to show that when you want to measure the voltage at a certain point on a circuit, on a basic, especially like this, a basic series circuit, you probe the area that you want to see, the potential of the drop that you want to see across whatever load there is, and then you put your other probe to ground. And I mean, obviously, I think you can guess what would happen if we attach probe 1 to the left side of the first bulb there. What do you think the voltage would read? Well, what you've essentially done there is you've attached, in parallel, you've attached your voltage, your voltmeter, across the battery. So you're just going to get the potential from one side of the battery to the other side, right? All right, the other way you can think of, because it's such a convenient example to talk about, I would like to talk about voltage dividers. And the way these light bulbs are arranged right now, they actually have arranged voltage, a common arrangement of a voltage divider, the basic voltage divider circuit. And it's the voltage divider comes into play when you want to change the voltage at a given point. You can change the resistances of two series resistances, and as a result, you will get, if you do it properly, you will get a different output voltage. You will read a different voltage. So, for example, we're going to call R1, light bulb 1 on the left there, R2, the right-hand light bulb, and we'll just say that R1 plus R2, are going to be always, R1 plus R2 is always going to be constant. So if I increase R1 by the same amount that R2 decreases, if I just change them the same amount but in opposite directions, then the voltage displayed on the meter, what is that going to do? Do you remember from the video what happens there? So you remember from the video that V out, so the spot in between the two resistances where you're measuring from your voltage divider, V out is equal to V in, which is the total voltage that you're supplying. So in this case, it's from the battery. And then you multiply that by the second resistance, or the downstream, you could say, resistance, divided by the second resistance plus the first resistance. And if anyone can derive this equation, I would love to see someone do it. Bring it up to me or a mentor. And the hint is that all you need to use to derive this formula is simply V equals IR. Okay, and you have to get a little bit clever with it, but I think you could probably do it. So see if you can arrive at this equation in blue here for the voltage divider based just from using V equals IR. All right, and don't Google it because that's cheating. But yes, the voltage is going to decrease. V out is going to decrease because, like I said, R2 plus R1 is constant. We're going to say they change the same amount but in opposite directions. So that means the only thing changing in the equation to the left there, other than V out, is R2, right? And R2 we said is going down. So if R2 goes down, V out has to do what? Yes, it has to go down because they're equal to each other, right? All right, let's just give this a shot real quick. I'm not sure what all you can see, but I want to show you guys how to use a voltmeter real quick in case you don't already know how, and even if you do, it's never too late to refresh. So first, I'm just going to connect. Really, this looks like a series connection, but it is in fact not in series because we didn't get into the finer details of the voltmeter, but the voltmeter has what's called a very, very high impedance. And so actually you can think of it as there's not actually any current flowing through the voltmeter. But that's beside the point. The point is that this is indeed a parallel connection you can think of, and the voltmeter is reading, what is it reading? Approximately 8 volts, right? And so now I'm going to plug this guy into, I don't know, hope everyone can see, but I'm plugging this into a potentiometer. And a potentiometer is a voltage divider that you can change the resistances by turning a knob. All right, you should all have one of these in your packet, and I encourage you to try this circuit out too. You really literally just follow the circuit that we drew up on the previous slides there. Just hook that up in your breadboard, and if you need to cut off these little metal tags, you can have a mentor help you cut those off with a pair of snippers. So remember, there's the center tap. Remember the center tap in between. So you can think of inside this potentiometer 2 resistances, right? And we are using this wire is tapping in between the 2 resistors. So I'm going to attach my positive lead, my probe 1 to that, and I need to connect this ground. Remember my ground pin, probe number 2. I'm I'm going to connect that to ground, right? And now we're reading, okay, so like 0 volts. And if I can hold this in place, we will change. So I'm rotating the potentiometer. And if you can see on here, the voltage is changing on my voltmeter. I don't know if you can all see that. Now we're at 5 volts, 6, 7, okay. Almost back up to 8. So what this is doing is changing the resistances with respect to one another, and my center tap is reading a different voltage as a result. Okay? Alright, so that was a good little lesson on voltage dividers, and I want to put in real quick, I don't want you guys to worry if you're not grasping all of the voltage and current relationships. It takes a long time to get the stuff to really settle in and to gain intuition about what's going on with circuitry. Even I and other mentors still struggle with the concepts and knowing things intuitively. It really it is kind of an art, and it takes a lot of time and practice. So don't worry about that. We're just getting you guys introduced, and it'll feel even more comfortable as the week progresses. So you guys are doing great. Hope you're excited to move on to the next portion of trying to figure out how to make this digital nightlight. So next up are phototransistors, and a lot of this V equals IR business is going to translate over to understanding the circuit involved with our nightlight circuit. Okay, so hang in there.